Hello, this is Mr. Stansbury. I'm going to take you through the 16D notes on exponential decay. At the end of this, you should be able to say I can solve real-world type problems using exponential decay equations. All right, so first thing, example 4 from page 526. The dancing cats from example 3 find an old pan of mama's spaghetti sauce. The cat population declines by 13% per week after eating the sauce. If the population was at 10 million before eating the sauce, find the following. A, write an exponential equation representing the situation, not this situation. So we're going to write an exponential equation. So what we can do, if we remember from chapter 13, we have A equals P times 1 plus R all to the n, right? A is the current population in this case. P is the original population. 1 is 1 plus rate as a decimal, and then n is the number of weeks in this situation here. So, excuse me. So, let's put C for the cat population. Initial population is 10 million. Oops, don't need that. And then we have 1 plus the rate is 13%. But since it's declining, we're actually going to subtract the rate. Okay, so we'll do 1 minus 0.13 all to the n. So cat population is represented by 10 million times 0.87 to the nth power. And that would be our exponential equation. All right, and we're going to use that on the next one, which is how many cats are left after 10 weeks. So cat population, 10 million. Times 0.87 all to the nth power, and now we're going to plug in 10 for the time, which is n in this case. All to the 10th power. We bust out our calculator and we do 10 million to the 0.87, sorry, times 0.87 to the, in this case, the 10th power. And we get 2,484,234 cats about. So 2484234. And that again is a guesstimation or an estimation, roughly, that many cats after 10 weeks. All right? Okay, let's take a look at another one here. Excuse me. We're going to graph the function. And so, again, you're going to always want to put your time on your x-axis and your other variable on the y. So, in this case, the population. So, let's put our equation in here, which is 10 million times 0.87 to the n, where n is the, again, the weeks. Okay, so if you put a 0 in for n, that's the original population, which is, we already know, is 10 million. So there's one population point. We just did 10, which is 2484234. 2484234. So that's the 10. And now all we want to do is just go back in here, excuse me, in here, and we want to use this entry here, and we're just going to change this to 5. We want to do it for 5 weeks and for 10 weeks. So let's do 5, and that gives us 4,984,209, 4984209. All right, there's all our apostrophes are commas there, and then let's do change this 5 to 20, and we get 617,142. All right, so we get all those data points, and now we can just graph those. So 0 is at 10 million, so there's 0. There's 10 million. 5 weeks is about 5 million. Just a smidge less than that. 10 weeks is at 2.48 million, so about 2.5. Okay, about there. And then at 20 weeks, 617, so not even a million, just like a little bit up from there. All right. Then we take a graph and try to make it fit through there, and that's pretty close-ish. And you can see the asymptote here is going to be 0. The population is never going to go below 0. You can't have negative cats. All right. Okay. Let's take a look at a short video here, and then we'll finish.
I've been to one opera, which I liked. I just didn't know what was going on. It was like another language or something like that. So I wish I would have an interpreter come out between the lyrics so you could follow the story, you know? Like the big guys out there. He kind of likes her. But she's really not paying any attention to him or anything. Something about his boot and a radiator.
All right, anyway. Excuse me, last question here. How long until we reach 10 cats? Okay, so now we know that here, let's start with our original equation. C equals 10 million times 0.87 to the n. Right? And remember, anytime it's less than 1, that means decay. Anytime it's more than 1 in here, that means it's growth. So again, it's declining because they ate the lovely pasta sauce, and so that's why it's less than 1. Anyway, we want to know when the population reaches 10 cats. So that's where the C in for C goes 10. So 10 equals 10 million 0.87 all to the nth power, right? So first thing we got to do, divide both sides by 10 million. Right? And we get some terribly small decimal divided by we get 1 to the -6th, right? So basically 1 over, let's see, one of those zeros cancel out. 1, 2, 3, 4, 5, 6. Oops. 1 over, excuse me, it should be a million, right? Because we just divided by 10. Yeah. Oops, I missed that 0 there. That's why. Okay, so it should be 1 over a million. So then we want to know when the population is 1/millionth of the original population equals 0.87 to the n. So this is where you're just going to want to log both sides, right? So log 0.87 to the n equals log of 1/millionth. That n comes out front. Let's take this whole thing over here. So we have log of 1 over a million equals n log of 0.87. So divide both sides by log of 0.87. And then we're in business. Right? So let's do this. We're going to do the log, there it is, of 1 divided by a million, which gives us -6, and then we're going to divide that by the log of 0.87, and that gives us 99.2. So it's going to take just over 99 weeks, right? Because this is all in weeks. Yeah, so it's going to take about 2 years to get down to 10. All right. So, really, that's all there is for this here. If you have any questions, please ask. But now you should be able to say I can solve real-world type problems using exponential decay equations. All right, thanks.